Okay, so we're going to start on chapter 6, which is on two-way tables and also on Simpsons Paradox.
Simpsons Paradox?
Yep. Which I can't, well, that's the best part of the chapter, Simpsons Paradox. Okay? So let's talk a little bit about what is a two-way table. Now the funny thing is I've already introduced this to you, but I didn't formally define it last time. So a table is basically where you compare two categories with one category as columns and one category as rows. Okay? So for example, let me go ahead and share my Excel here, and if you guys want to follow along, that's fine. That would be great, actually. I swear they've changed this. It's driving me crazy a little bit. I'm just doing a blank one. So, and I'm trying to decide, well, we actually did one last time in class, but I'm going to pick a different example this time. So we'll pick example 6.1 if you want to follow along on page 164. These are academic degrees by sex. Okay? So one way we could do is we will put the degrees across the top, associates. So this is one categorical variable. What kind of degree do you have? Associate, bachelor's, master's, and professional/doctorate degree. Okay? So those are my column headings. And now we're going to do our row headings, which is sex. So I've got women and I've got men. Okay? So the raw numbers are 673, 401, 1050, 780, 481, 342, 95, and 89. Okay? Now one of the things I always like to do is I always like to center all my data, and I like to box it so that it's in a nice table. Okay? So here's your raw data. Okay? Now, let's talk a little bit about the marginal distributions. Okay? And basically the easiest way to think of this, I wasn't super fond of the book's definition, but the row and the column totals, or I would also say you could do it as percents. But in order to get percents, what do you have to do? You gotta get your row and column totals, right? Okay. So let me share my screen again. Okay. Could change this thing. All right. So the reason why we call them a marginal distribution is because you could think of the total here as being in the margin of your paper. Okay. So once again, we can add up the row. So we've got 2,299 women. I'm going to copy that and I'm going to paste it on the next two lines. Okay. And we can also do the row totals. Okay. So I'm going to add up the associate's degrees. I'll center it because I think it looks better. And we will copy that to the others, okay? So one way to think of the marginal distribution is, well, what percent of people are women in this table? How would you figure that out? So I could do, we'll do this, okay? So I've got the 2299 women divided by the grand total 3911, works out to be that 58.7% of the people in this table are women. And how would I do the men, Brenda?
You're just doing the total times the row total times
The row, I'm just trying to find out what percent of people are men in this table.
Oh, so just total divided by the.
So tell me what to click on.
So 1612.
The 1612 divided by all the total people. So we got 58% are women, 41% are men.
So wait, just the percentages right now, or the marginal distributions, right? Like the total marginal distribution.
So these are both in the margin, right?
Oh,
So I've got the marginal distribution, so I've got the total here, and then I've got the percent. Okay, we could.
You have to have the total and the percent. That's they both.
You could do, so the book kind of just says the totals, but usually you're going to want to know the percents as well. So let me ask you, Tanner, what percent of people have associate's degrees?
So you, to find it, you have to take 1074 and divide that by 3911.
Okay, 1074 divided by 3911 would be 27% of people have associate's degrees. Now, by the way, is there a nice, easy way to copy that? What'd you say? We need to F4 the second number, right? What happened to my formula? This version of Excel is kind of goofy here. We'll do that again. The 1074 divided by 3911, and we're going to F4 that one. So that puts that in there. Okay? Now, when I copy this to the right, we can see here. Okay? Now, what should these percents add up to?
100.
Hopefully they'll add up to 100%. If I add up that row, it's 100%. And if I add up this column, it's 100%. So that's one way you can check yourself. Okay?
Are you recording right now?
I am recording it. Okay? So does the marginal distribution make sense to you? Okay?
So the marginal distribution, I can't speak today, is the whole total, and then the percents, and then.
Yeah, the totals and the percents. Okay? Now these are some slightly different calculations than we did last time in class, but they're also useful. Okay? Now let's talk a little bit about a conditional distribution. Okay, I'll try to follow the book's definition a little bit, although I'm not a super fan of it. But the conditional distribution here is the distribution of values for only one variable. I think that's probably the easiest thing to do. Okay? So as we go back to our data here, Okay. One thing we could say is we could do the conditional distribution for the percent of women with each degree. Didn't mean to center that one. You might want to left justify that one. Okay. So what percent of women have associate's degrees? How would you figure that out?
So you'd have to do 673 divided by your total of the column, which is 2299.
Okay, so 673 divided by the 2299. Okay? And I'm going to F4 that because I'm probably going to want to know that for all the variables, right? So one way to do so one version of a conditional distribution would be just to figure out the percent of women, okay? So 29% of women have an associate's degree. As I drag that to the right, 45% have masters, 20.9%, have bachelor's, 20.9% have bachelor's, and 4% have professional or doctorate degrees. We could do the same thing. I'll try to spell it right now, I won't. For the percent of men, right? Okay. And how would I do that one, Jalen? You didn't know? But you're going to walk out of this class knowing. That's the best part of this. Because Brady's going to help you. No, we're going to have, Kensley's going to help you.
Okay, so you take the 401 and divide it by the 1612.
1612, okay. So now that you've seen it once, Jalen, what percent of men have bachelor's degrees? C4, which is 780, divided by 1612. Okay? And if I F4 that, I don't have to redo that every time, right? I only redid it because I wanted to make sure you learned. So I succeeded. Jalen's learned something today. Okay? All right, does that make sense?
Is this what our quiz is going to be on?
No. Well, it will be your quiz on Tuesday. All right, so that would be an example of a conditional distribution. Now, there are a couple of other interesting graphs in here. In the book, they refer to this as the segmented bar graph. Okay. Now, when you guys are doing your poll, I don't know if I like this graph, but it's something here. In Excel, we call it the stacked bar graph. Okay. So Excel has a different name than the book. But one of the things that we can do is it might be interesting to see how the men and the women compare. Okay. Segmented bar graph, each category is 100%. Okay, so let me show you how to do that. So what we'll do is we'll highlight our table. I don't want the totals though, I just want the raw numbers. Okay, and what we can do is we can insert. We're going to go to column graph here, but this time we're going to click on the third. Now this would be a bar graph. And to be honest, well, let's compare these two. So this is a traditional bar graph. And then we have, let's do the same thing again, highlight this. I'm going to say insert, click on this again, but we're going to pick the third graph this time. Okay. Now, so this one is the segmented slash stacked. Okay. And then this is your traditional bar graph. So let me ask you guys a question. Let me show you this in the book. But of these two graphs, they both kind of tell you this. Well, there's advantages and disadvantages to these. Which graph do you like better?
Right.
I do too, the right one. Okay? But the problem with the one on the right is it doesn't let you know what percent have each degree. Okay? So, and to be honest, this isn't the best graph to do this on, but one of the things that you can do, if you look at the graph on the left, you can see here when we talk about associate's degrees, you can see here that more than 60% of women are in blue. They did that backwards. Men should be blue, right? Women are pink and red. Anyway, Excel did this backwards. By the way, do you guys know how to change colors if you want to change colors? You may want to do this because here's what I will say. The independence test that we learned last time in class is very useful for your M&M project. And so a lot of times you'll put red, blue, green, whatever, and then it'll pick different colors. And so if you want your red to be red and your green to be green, this is what you can do. So if you, I think you double click. No, let's try this again. You can go over here and you can change the color for the fill color.
So top left says change colors.
Oh yeah, I guess you can do it that way too. And we can turn the men or the women. Let's see, I'm on the women. We could make them. Let's make them pink, right? Don't they have more colors? Okay. And now we can do the same thing with the man, and we can change them to blue. What happened there?
It gives you like a palette.
There we go. Okay, so you can do it that way. Okay, so now we've got the women are pinkish red and the men are blue. Okay, so the interesting thing that you can see here with the stacked bar graph that's a little different from the regular bar graph. Number one, so there's benefits to both graphs. The advantage is you can see that by far bachelors are the most common degree, okay? But you don't know the percents very well. And so what you can do is you can see, for example, the women are above 60% on associate's degree, whereas in professional degrees, they're just barely over 50%. Okay? So these you're kind of able to compare the percentages a little bit better. Now, let me throw out a third graph on here. And we'll probably want to change those colors too. I haven't tried doing a pie graph on these.
You upload this to Canvas?
Huh?
Did you upload this to Canvas?
Not right now, but I can later.
Oh, yeah.
So this pie graph looks a little goofy. I would probably, in fact, the way I did that, it probably might be better to do the women's pie graph. And then we could compare to the men's, okay? So here, I'll highlight this, and if you hold the control key down, we'll do the men's, and we'll say insert pi, 2D pi. So there are lots of ways to display your data, okay? Would it be a good idea to do a histogram on categorical data? No, why? Categoricals are not histogram. What are histograms used for? Quantitative data, okay? So remember, by the way, has everybody collected all of their data by now? Who has not collected all of their data? Okay, we're getting down to the end here. Let's get that done. But as you're looking here, when you're thinking about graphs to use, make sure you're using appropriate graphs. So you can choose a pie graph, you can choose a bar graph, you can choose a segmented stacked, or a histogram, but make sure you're using a histogram when you're supposed to use a histogram, or a pie when you're supposed to use a pie, or pies and bars a lot of times you can whip around. And in some cases, I think where you have a high contrast, so for example, I'm going to change this number here, it'll be like 10, okay? a segmented bar graph, if this was the numbers, you could kind of see, wow, there's something going on here. Women are getting a lot more professional degrees. So if you can see a high contrast, this data isn't really good because there's not a big high contrast there. I'll put that number back the way it was. So the segmented chart can be very useful if you've got, like, a lot of women get associates, but very few of them get doctorates, or vice versa. Yeah, something like that. That's when the segmented or the stacked bar graph is more useful. Does that make sense? Okay. All right. So, anything else I'm supposed to? Oh, you know what? There's one other graph that they talk about in here. Excel doesn't actually make it, but it's called the Mosaic Graph. Okay. Or Mosaic plot. The mosaic plot is kind of interesting, but one of the interesting things is the bars have a different width. Okay? I haven't done it yet. Okay? Now, note, Excel can't make this graph. Okay? So in your book, so look on page 169. In fact, maybe I will stop sharing for a moment. This here, I'll put this up to the camera so you can see it. This is a true mosaic graph here, okay? And you can see that they have different widths. Now, one of the advantages is, as opposed to the stacked bar graph, see the stacked bar graph, you can't tell the associates, bachelor's, master's, and professional degrees are much different numbers, okay? You can kind of see that with, when you compare the bar graph, you can see that especially since we're doing totals, and by the way, I didn't put in titles here, right? Make sure you put in your titles or I'm going to mark you off on your test, okay? So, what should we put in here for axis titles here? Number of degrees. And down here?
We have type of degree.
Education level. Yeah, or type of degree, that would be fine. Okay? So make sure you're doing that. Now, one of the nice things about the bar graph is you can see bachelor's degrees are where it's at. That's my biggest number. So one way to kind of combine the stacked bar graph with the traditional bar graph is to do what's called a mosaic graph. Excel won't do that, but the closest thing that it will do is, if I highlight my data here, this is going to be, if you click on this one over here, the next one over, it calls it a tree map. Okay? So this is as close as tree map is the closest to the mosaic. Okay? It's not exactly a mosaic because the problem is, look, the professional and the masters, they stack each other. And it looks like the professional and the masters are equally wide, and they should not be, because when you look at your table, you've got 800 versus 184. So these should not be the same width. But basically, the idea here is you can see here that the bachelors are the largest, associates are second largest, masters are third largest, and professional degrees are fourth. But they should not be on top of each other. They should be side by side. And the professional should be much thinner, about 1/8 of the size of the master's degree. So this is the closest we can get to the mosaic because Excel won't make the mosaic graph.
And on these tree graphs, I see that there's no space for axis titles.
That's correct. Well, actually, let's see what happens when we try to add them. Yeah, you can't add them. So I don't know that I'm going to, the book mentions it, so I'm mentioning it here. That's the closest you're going to be able to do to that. So I'm not probably going to focus on that very much because you can't make it very well. Brady.
Okay, so which ones do we need to know for the test? Which graphs? Do we need to know the traditional and the segmented?
The traditional, the segmented, which Excel calls stacked.
Okay,
I would like you to understand what a mosaic graph is, even though we can't really do it.
okay.
And I would also like you to know the, here, let's put this over here in the pies. Because to be honest, I love the pie graph. In fact, I would probably prefer the pie graph over the stacked bar, unless you have a wide disparity. Like I said, let's pretend that the men were 10 here. And let's pretend here that we're going to boost up the women to be 1,000. Okay? Oh no, we don't want to boost the women here. We're going to boost the men to be 1,000. 10,000. See, in this case, now you can see some big differences here. And so this is kind of useful if you have big differences. Because you can kind of see, wow, the women are getting all the PhDs, the men are they're hardly getting any associates. Okay? So that's kind of useful when you see that. Does that make sense? No?
How do we change that graph?
It just changed because you changed the
I
data.
changed the data.
Yeah, you changed the data.
Okay, I was like,
Yeah, I changed the data. I changed the data to create contrast. Okay? Now, clearly you're not going to change your data, but what I'm trying to illustrate, look, we've got 10,000 men with associates and only 10 men with doctorates. So you can see the women are getting, what, 90% of the professionals, and they're only getting 5% of the associates. Okay? So that's where the stacked bar graph is more useful. Okay? All right, now, what time is it? We got 20 minutes left. Here's what I'd like to do. The last thing I want to cover in chapter 6 is what's called Simpsons Paradox. Now, if you go back to Canvas here. And I'm pretty sure, did I post that as an announcement? Yes, the spreadsheet that we worked on last time?
I think you might have uploaded it. I guess, I don't know.
All right, let's see here.
Teach them math 1050?
In the summer, I will be. You gonna come?
No, I already took that class. I passed. That's all we need to know.
All right. No, I think I put it under worksheets. That's right. So if you go into in-class worksheets here, you go to the bottom, and I've got the chi-square university here. So this is the same thing we worked on last time. Okay? Now, just as a review, okay, so let's just review what we did last time. Go ahead and enable editing. Okay, so remember last time we did the marginal distribution, but I didn't tell you that's what we did. Remember we did that at the very beginning, and I said that was much too easy for this class? Well, it was actually chapter 6. Okay, so we've got men are being admitted at 43%, women at 33%, right? First, it looked like there was some discrimination. It looked like men were being treated better than women, right? But then we did this whole hypothesis test, and we said there is not enough evidence of discrimination against women. A better conclusion would be that there is not enough evidence that admission rate is not independent of gender. Okay? So it looks like women are not being discriminated against. Okay? So I think I've told you the phrase by Mark Twain, lies, damn lies, and statistics, right? So women, does it make you wonder if these numbers might not be correct? Like, there's got to be some discrimination going on, right? Doesn't this seem like there's a 10% difference here? Why are we saying that there's not discrimination? Well, that's exactly what the University of California at Berkeley did. And so let's go over here. This is an example of what we're going to call Simpsons Paradox. Okay. So Simpsons Paradox, I do have this here, basically says, doggone it, where's my thing? All right, they said, okay, so here's what we're going to do. We are going to take these numbers here, and we're going to look at these, and so we're going to look at the engineering department. Okay? And we're going to look at the admission rate in the engineering department. Okay? Now, in the engineering department, I don't have my notes here, so I can't remember. But I believe there were 30 men admitted, there were 30 men denied, and there were 10 women admitted and 10 women denied. Okay? What's the admission rate for the men? It's 50%. What's the admission rate for the women? It's also 50%. You guys didn't even need to use a calculator to figure that out, right? So they said, okay, so clearly there is no discrimination in the engineering department. Okay? So they said, well, since there's only 2 departments in this university, there were actually 6 at the University of Cal Berkeley. It must be the English department, right? So they went to the English department and they said, give us your numbers. Okay? There were 5 men admitted. There were 15 denied. There were 10 women admitted. There were 30 denied. Okay? Now, let's practice our marginal distribution because this one's not quite as easy to do in your head, right? We should figure out our totals, right? So if I get my sum here, 20 and 40, okay? Now, when we do the admit rate here, it works out to be 25%. 5 divided by 20 is 25%. 10 divided by 40 is also 25%. So there is no discrimination in English. But here's what the Simpsons Paradox does. Now I think if I add these up here, I never did my totals. I'm doing this from memory because I couldn't remember. Does that add up to 80? And that adds, oh yeah, that adds up to our 140. Nice! I did this from memory. I can't believe that worked. But Simpsons Paradox says that associations can reverse when smaller groups are combined with larger groups. Okay? Now, in this case, they didn't reverse, but they could reverse. Okay? So the nice thing about here is I've got 80 and 60 adds up to be 140. So I remembered my numbers. I've done this enough times, I remembered them. Okay? So the problem is the engineering department is much bigger and it's got many more men, right? So even though there's no discrimination going on in engineering and there's no discrimination going on in English, okay? The problem is when you combine the groups, because the engineering group has more men than the smaller English group, which has more women, it gives you the impression that there's discrimination going on when in reality there wasn't. Okay? So this is an example of what we call Simpsons Paradox. Now, the funny thing about it at Cal Berkeley is it did actually reverse. I'm going to copy these formulas here for a minute, okay? And I believe that the men Let's change this to 29 and 31. The men had a worse admission rate, and let's change this to 11 and 29. And the women, so now what's going on? Women have it better in the engineering department, and women have it better in the English department. Yet, when we go back to here I'm going to dump this by 1, 34 and 46 and 21 and 39. Okay? So it still looks like men have it better, right? But now, when we look here at Simpsons Paradox, women have it better in the engineering department and women have it better in the English department. But it looks like they've got it worse in the overall. Isn't that interesting? Okay, there was actually a lawsuit by women at Cal Berkeley. So here's the funny thing. Let's look at Cal Berkeley. There are more women, so typically at most universities, there are more women nurses than men nurses, right? They wanted to change that, so they actually encouraged men to get admitted. In engineering, there are generally more men than there are women, right? So they changed their admission so that women had higher admission rates than the men in the engineering department. And they did this in all the cases that were dominated by one gender, they tried to allow the other gender more admission to it. And so in every case, it was reverse discrimination going on. And the women actually had it better in certain departments than the men did. And so that's an example of what we call Simpsons Paradox. Okay? So the perfect example, yes, it looks like the women have it worse, but in reality, they have it better.
Will you click on like the 48? Okay, me too. Okay.
How does it look like one of those smaller ones?
And the reason why this works is because the engineering department is larger, 80 versus 60, and the men are larger, 60. So 3/4 of the men of the 80 applied, whereas in this case, 2/3 of the women applied in the English. Okay, and so the problem, this happens when your sample sizes are uneven. That's really what it means. Okay, so when your sample sizes are uneven, the associations can reverse. Okay. All right, now I've told you everything I want to know, or I want to tell you today. So the question is, do you feel ready for your quiz, or do you want to review for 10 more minutes before we take the quiz?
Let's go back through the notes from last time. Or just walk through.
Okay, so here's what we can do. We have this other thing here, okay? I'm going to copy this over here. Oh, except for we need to change these numbers back. What was this number? 780? And this one was 89.
401.
What's today?
401 and 780.
Oh, you're right, 401. Okay, all right. So we've got 10 minutes before we're going to, because I want to give you 15 for the quiz. Okay, so here's what we're going to do. We're going to do this fairly quickly, and we're going to do a hypothesis test. What would be the hypothesis test we would do in this case? Here, let's go through our steps. Find the numbers, right? Step number 1, find the numbers. What numbers do I need to find in this case?
You need to find the totals of each column and then totals of
Each column in a row. Okay? So I'm going to copy all of these, and I'm going to copy this, bang. Okay? All right. Step number 2. Categorical or quantitative. and it's categorical. Okay? Step number 3,
Find null and alternate.
null, alternative hypothesis, null, and the alternative. What should the null and the alternative be? But don't just say independent. What's independent of what?
Gender and.
Gender is independent of degree. The alternative is not independent. Is it okay to put dependent?
No.
No. Because there are lurking variables like Simpsons Paradox going on probably. Okay? 4.
Which has to be the Greek word, I don't even want to pronounce it.
I don't want to say it wrong. It is Z, a T, a chi-square.
Yep.
Yep. One of those.
Yeah, I'm like, okay, no.
It's a chi-square test of independence. And there are actually more than one chi-square test. You're only going to learn one though. But there are other ones out there. Okay? Chi-square test of independence. So how do we do that? We're going to call this the observed, right? Okay? Well, you're not going to have to do this whole thing on the test, but you're just going to have to interpret on the quiz. Okay, so let's erase our data. This is now called the expected, right? And then
So then you take.
we're going to do the observed minus the expected.
Unexpected, wouldn't that be the total times, total of the row
Total of the row,
times the
total of the column,
total of the column
Divided
divided by
by-
the total?
grand total.
Yeah.
Total of the row, so now I'm on the second row, times the total of the first column divided by the grand. Equals the total of the first row times the total of the second column
So it
divided
doesn't
by the
matter
grand.
if you do row or column first. So you can either do F, you can do C4.
I would, it doesn't matter, but I would, so you don't make a mistake,
Okay.
I would be very deliberate about this.
Okay.
Row 2 times column 2 divided by the grand equals row 1 times column 3 divided by the grand equals row 2 times column 3 divided by the grand equals row 1 times column 4 divided by the grand equals row 2 times column 4 divided by the grand. Okay? Now what?
Observed minus.
And this is where you gotta use parentheses or you'll get it wrong.
Observed minus expected.
The observed minus the expected quantity squared divided by the expected. Okay, now can I show you a little cheater trick, especially since we're in a hurry?
Yeah.
You can copy this formula and it will work.
Are you kidding me?
You cannot copy these formulas though. You have to do those.
Okay.
But this third table, you can copy them and it will work. Okay? Second table, sorry. Can't. Okay, then I need to find the sum, right? So I'm going to find the sum of this entire table, which works out to be 12.09. You guys remember what your degrees of freedom are?
Wait, just really quickly, where you click on like the associated limit, can I sort of just see that division?
This one here?
No, sorry.
This one here?
So you do observe,
Observed minus expected.
oh,
Squared.
square,
Minus
oh.
expected.
Divided by that same number again, 631.
Oh,
Okay? You're not going to have to do this because I'm not, well, I guess I could have done it on the computer today, but I didn't. Okay? All right, so now step number 5 is what?
Reject or not reject.
Nope, you're missing a step. Find the p-value.
Chart or computer.
We'll use the computer for now. Oh, actually, let's do it both ways. for the computer is, what is it? Chi-squared dist. Is it right-tailed or left-tailed?
Right, it's always right.
Always right. Okay. What do I put in for x? 12.09. What do I put in for my degrees of freedom? 3 degrees of freedom. Do we know why it's 3 degrees of freedom?
Because it's 4 minus.
4 minus 1 is 3. 4 minus 1 is 3. So that's the 4 columns. And 2 minus 1 is 1. 3 times 1 is 3. Okay? So I got a chi-square of 0.007, which means, well, let's do it on the chart too really quick. File, open, is it open? Oh yeah, it's here. How would you do this with the chart? 3 degrees of freedom. We got to find 12 on here. 12.09, it's in between those two numbers, right? Okay, so your p-value is in between 0.005 and 0.01.
You always work it out so that it's somewhere on that chart. Does that feel like on our homework?
Well, what if I had gotten 13 on here?
What if you would have gotten like 20?
What if I would have gotten 20?
I feel like on the homework they were like way off the chart.
Okay,
Like,
there's 20 on
no, but not in the row.
Yeah, 20 is not on this row, is it?
it. Oh, no.
So what would be the answer if it was 20?
Based on the charts, there is not significant.
Less than 0.005. That's all you would
Oh, you
need.
just say less than.
Yeah, in that case.
Oh.
Okay?
Oh, because it's always.
Because it's beyond, it's bigger than this number, so it's less than that number. Okay? All right, so now, step number 6.
Step number 6 is reject or do not reject.
Reject or not. And the answer survey says reject, because p-value is much lower than my alpha. What was my alpha? I didn't say.
0.5.
Equals 0.05. Or the slalpha. Whatever, I can't type. Okay, and step number 7.
We didn't go over step number 7.
Yeah, we did.
Write it out in English.
Write it out in English. So there is or is not.
There is.
There is evidence that
Gender is not.
Not
Independent.
okay. Now, bonus. Do you want to know extra? You want extra credit on this?
Change the color of the graph.
We say it's not independent. What is the biggest numbers that are out of whack? Okay. So as you look at this 12, which of all these numbers here is the biggest number that contributes the most to the 12? The associate's degree. So as we look at the associate's degree, okay, we expected 442 men. We only got 401. What does that mean? Fewer men got associate's degrees than expected. What's the next biggest number? The women associate's degree, okay? We expected 630 and the women got 673. More women got associate's degrees than expected. What's the third highest number? We'll stop at 3. Men doctorate, okay? So we expected 75.8, we got 89. What does that mean? More men are getting professional degrees than expected. So men are getting, so here's kind of the key takeaway here. Men are getting fewer associate's degrees and more doctorate degrees. Okay? So that's kind of interesting, yes? Okay. All right, well, we've got 15 minutes left. Hopefully believe we've answered all your questions because it's quiz time.
All right, good.
Okay? So, put everything away. I'm gonna stop recording. Do you have a quick question about this?
Yeah, how do you get the chi-square one more time? It's equal, then the thing with the right tail.
The chi-square, you add up all that stuff.
Oh, okay, well.
Okay? All right.
Can you give us a formula sheet?
Why?